panels that have been built on top of these.
Start. Good morning, everyone, and welcome to the last session of this long conference, a very interesting FRINGE 2023. My colleague Samuel Bancroft from the University of Leeds and myself, Michele Mantone from German Aerospace Center DLR, will share this session. And I would just start introducing the first speaker, which is Ru Wang from University of Wuhan. We give a talk about the exploitation of multitemporal INSAR for monitoring of infrastructure information. So please, the floor is yours.
Good morning, everyone. I'm Ru, and I'm happy to share my work about monitoring and interpreting deformation along linear infrastructure using deep clustering of anti-INSAR analysis. And for the specific transportation infrastructure like railways, MATLAB, the monitoring and interpretation, the only velocity distribution is not sufficient. So the time series analysis could do better, including the classification. The existing proposed method mainly based on known functions or temporal evolution models. They are powerful, while they predefined temporal evolution models could make it too restrictive for detection of unknown temporal patterns. So the deep learning method proposed recently made an advance, while this method couldn't consider the spatial point of each point. So here we use the spatial-aware deep clustering method composed of the variational autoencoder model with the LSTM layers. And we also add the geolocation to make the cluster result more reliable. And we choose the two baseline methods, the DTW distance-based k-means method and the UMAP plus HDBSEN method to cluster as the comparison result to discuss. Firstly, we test the method on the synthetic data. The simulating dataset is mainly composed of four typical types of temporal evolutions. And in terms of accuracy, just random index and normalize the mutual information, we could find the VE cluster method could have the better performance than the baseline method, and computer matrix also showed a similar conclusion. Then we test on our real data set. Case study 1 is the Tianjin Railway. The data set, the result is from the Tesla X from 2030 to 2090. But before the clustering analysis, we found the unwrapping phase in the interprogram could still be with unwrapping errors, like in the left figure. So in this way, we assume the phase is continuity in the time and use locally weighted linear fit to fit the temporal models. In this way, we can locate the phase jump with integer multiple of 2 pi and reduce the jump phase of the integer multiple of 2 pi and re-estimate the other phase contributions like atmospheric phase to get the deformation phase like the right one. And in the time dimension, we also found the phase unwrapping error is reduced by this method. And here we get the typical deformation velocity map and the corresponding deformation time series. We could say even the B and C, the deformed points, but they have different change in the detail. Like the C is firstly with larger velocity and then comes to stable. So the first result is based on the dTW distance-based K-means method. It can identify different trends along the lines, but the K-means the distance is calculated on the high dimension of the time series. So the detail or the detail features of each lines could be hinted if we calculate the distance directly on the high dimension. So we could only the K-means hardly found the subtle features or subtle difference between different evolutions. And the second method is the UMAP plus HDBSAN, because UMAP is used to dimension reduction of the height of the time series. So it can find different temporal, like the cluster 0, 1, 2, and 3. The subtle difference could be identified, but the most question is that actually the most of the point is in cluster 7 is mixed in the biggest one. So because the UMAP is also quite sensitive to the parameter decision. And the VE method is actually, it is multi-task models, except for the cluster, it also can reconstruct the time series. So in this way, the reconstructed time series could reduce the noise to somehow, even though the phase unwrapping errors has been reduced at the very beginning step. And this is the our method to get the result. It can identify different patterns, and for cluster 1, it also can identify the relatively complex with the velocities also changing. Yeah. And the case study 2 is Shanghai maglev, different from the Tianjin railway. The deformation signal is not strong at all. So, we used the 2 frames of tensor X data from the same orbit with the interleaving time, acquisition time. So when we process the data set, even in the overlapping area, even we choose the same reference point of the 2 frame, we could find the difference in the time points in the overlapping area. So to combine the 2 frame of time series is also unnecessary. Here we used firstly according to the very beginning one is from the unwrapping phase, reduce the DM errors and including the orbital error. And we based on the phase difference in the overlapping areas to estimate ramp phase in the other way to make the 2 frame consistently firstly. And then now we think the orbital error is in the whole areas be the same, and estimating the orbital error in the whole area could combine them together and also reduce the error components properly. And time series in the type point in the overlapping area processed by the steps software is shown in the above, and after the combined estimation of the orbital error, the two frame now gets consistent now. At the same time, we also have 5 leveling points around the lines. Due to the leveling point is on the ground, it's not along the track. So we choose the point on the ground in the buffer area to compare the velocity. And the maximum difference between the initial results and leveling data is no more than 3 millimeters per year. So it also validates the accuracy of the result. And this is gets the cluster result along the lines. We could find the temporal evolution is quite complex because the deformation signal is not so strong, and it's hard to use functions to fit each lines. And zooming into part of the lines, we could find there is a regular distribution of 2 clusters along the track. It is correlated with the track structure because the maglev track is built on the multi-span, and with the unit structure is the left one, and end pairs have strong stable requirements than the middle one. The orange cluster corresponding to the orange cluster. The orange cluster corresponding to the middle pair location. Yeah. And if we only use the velocity distribution, it's hard to find this interesting information. And for the geolocation background, because the track is built with the deep foundation in the deep piers with foundations, so it's quite stable compared with the surrounding areas. We only could find the land subsidence in the surrounding areas, and where the geological background and is more complex and weaker, the land subsidences occur. And we also have several well data along the lines. The FS9 is located on the very beginning of the land, and the cluster result found this cluster of the temporal evolution have some relationship with the water level in the aquifer 0, and aquifer 1 just shows the increasing trend. So we think the extracted cluster temporal evolution has more relationship with the water level in aquifer 1, and another well also shows the cluster result in the surrounding areas have no relationship with the groundwater level in the aquifer 1. So I think the aquifer 0 has more correlation with the surface displacement. And finally, we choose the case study 3, the railway in the Wakefield on the south of the Leeds, because in this study the temporal epoch is much more than before, high to 320, and from the velocity distribution, the deformation signal is a little noisy, I think. We couldn't only according to the one deformed point to say, this section is endangered, I think we can't. So I processed the series dataset into the latent space using the VE method. We could find there are several obvious different patterns in this dataset. So we also get the different clusters along the lines. This method, this result is without geolocation information, same to the deep learning proposed before. It can identify different patterns along the lines. The cluster 1 is corresponding to the former stable, then detrained, like this. But when we check the cluster distribution along the lines, it's quite not so regular, because maybe in the quite small length there will be different cluster. We can't identify the status of the every sections. So adding the geolocation into the time series dataset, we could make the cluster results have more spatial patterns, make the cluster result more reliable. And the weight of the geolocation is also a key point to discuss, because if I get the geolocation weight is too high, maybe the cluster result is mainly according to the geolocation without the temporal evolution. So to balance the two information is also important. Yeah. To conclude, I think first way to ensure the anti-insult processing to get accurate time series dataset is a prerequisite. And the spatial aware deep clustering on temporal evolution helps to interpret and analyze the time series data. And further analysis is needed to examine the various factors contributing to the deformations along the object we considered. That's all. Thank you and welcome for the questions. Thank you.
Okay, do we have any questions? Right there?
So just wait. I'm told to wait. Okay. Hi. I wonder if any of your clusters equate to a sinusoidal atmospheric contribution, because I couldn't see any. So could you comment on that?
You mean, have I reduced the atmospheric terms? Yeah, because I processed it built on the stamps, so they use the filter and spatial filter, temporal and spatial filter to reduce the atmospheric. And if the time span is quite long enough, I think the atmospheric term will be reduced as the time span enlarges. Yeah.
More questions? We have still some few minutes for starting the next talk, so.
Nice talk. Thank you for your presentation. And now I have a question about the number of classes. So I know that, of course, for k-means you have to select the previous number of classes, but for the other one, and in case you have to do for all of these approaches, what's the way you select the number of classes before running, of course?
The number of clusters is decided based on, because I can check the latent space, scatter distribution in the latent space, and I just according to there will be obvious different cluster, and according to that, to determine the number of cluster. And if I add the location to it, it will change the schedule distribution in the latent space. So just according to that distribution to determine the number of clusters.
So it's a semi-automatic procedure.
Yeah, I think it's semi because I should identify the cluster by myself. Yeah. Thank you.
Okay, thank you very much. We'll move on to our next speaker. We have Lama Duala from Canada University.
Hello everyone. I'm a PhD student from Padova University, and today I would like to talk about learning displacement signals directly from the RAP interferograms of Sentinel-1 using the aid of artificial intelligence. So let's start with an introduction about the challenges in implementing INSAR, the main objective, the implemented data sets, the initial and enhanced stages of the methodology, the results, and some final conclusions. Today I'm not talking about how INSAR revolutionized our ability to monitor and map the surface of the Earth, the terrain information, and many other geological phenomena. What I'm talking about is that this concept of INSAR, which appears to be simple at first glance, like a satellite comes to take an image, then from almost the same position comes back to take another image, and these images are compared to get the important information, is not simple. It's a complex process that requires deep understanding of both the technology and the science behind it. And of course, it's fraught with numerous challenges. So for example, if we just try to implement SPAS for a certain application, we all know that many steps of these steps are time-consuming and intensively computational. So any mistakes or inaccuracies can lead to erroneous conclusions and wasted resources. So that's, of course, in case we are sure that SPAS is the right technique for our application, because even choosing the technique is not a trivial task. Accordingly, other complexity layer and errors can be also a very problematic question to answer. How to mitigate this how to mitigate this screen over the image, the atmospheric phase screen. What is the appropriate methodology to use for phase unwrapping? To know what is the right number of 2 pi cycles to be added to the phase values to reconstruct your phase values. This is also a very complex question. So we have also coherent additions of scattered signals comes from different structures existed in the same resolution set. Spectral should be filtered. Thus, of course, you should know also the geometry between the radar and the ground, the surface of the ground. Otherwise, you cannot interpret the foreshortening layer of foreshadowing. What I'm talking about is that the role is challenging. Of course, the rewards like having submillimeter accuracy and 3D representation of the surface of the Earth well worth the effort. But why we cannot just have an indication about this deformation from the very start? For example, I'm a geoinformatic engineer, and in order to do any kind of monitoring for a structure, I need to go to that website, to that site with my instrument, with my traditional instrument, like the total station or any additional instrument to do some preliminary tests. So we cannot just develop a methodology that can circumvent these needs to go through all of that analysis to know something, otherwise we know nothing. That methodology can just leverage the RAP interferograms and coherence maps as its input parameters for identifying areas of motion. Before diving into the methodology, I would like just to take the chance to thank ESA for their generous sponsorship, because they provided us with the required data sets that we need, because we needed, of course, for our algorithm, huge number of data sets. The data sets that we used were from 3 different regions in this earth, which one of them was in Italy, Lombardy, and the second one was in Portugal, Lisbon, the third one was in Washington, in USA. All of these areas are sensitive to landslides, and that's why they have been chosen. I didn't know that all of the slopes are moving in Iceland, otherwise I would choose, of course, one of the cases here. So the service that we used by the geohazard tip was the parallel small baseline subset, which is the advanced version of SPAS. And these are the parameters, for example, for the Lombardy region, and here's the deformation map. Also, this is the deformation map of the Washington in USA. We have also this deformation map for Lisbon, and we not only needed the deformation map, but also the RAP interferograms, the coherence maps as well. Okay, that's fine. How can we do this? When we have a measurement point, the measurement point is spread all over the surface of the Earth. Let's imagine, instead of that the measurement points are spread all over the interferograms. But as we know, we don't have only one interferogram. In the time series, we have maybe 100 interferograms, 200 interferograms. So let's suppose that these measurements are spread all over the first interferogram in the time series, and here's the second interferogram, and the last. Okay, fine, I imagine. Then what? Let's study 3 measurement points. For example, the first measurement point, of course, is included in a pixel. And if I'm talking about wrapped interferograms, then the value of this pixel is between -pi and pi. So for example, it was this number. Again, the second measurement point has this phase value. And the third has, of course, a different value. It's the same for the second interferogram. It's the same for the last interferogram. Each measurement point is included in different pixels, which has different phase values. This is the training samples. So now we have a matrix which is composed of number of columns and number of rows. The number of rows is the measurement points, and the number of columns is the number of the interferograms. Cool. What about the labels? The labels are inferred from the velocity values of the measurement points. So we are talking about measurement points that has a velocity value, for example, -1.5 centimeter per unit. What could be the label? We created 3 different models. The first model is just to check if the measurement point is positively moving or negatively moving. So if the velocity value is -1.5, then the label of the pixel, which contains the measurement point, is negative. And if it's positive, then the pixel label is positive. The other model, to check if the pixel is fast moving, and accordingly we set a threshold of 0.7 centimeter per unit, because after this threshold we can see that the movement is quite recognizable. So if the measurement point has a velocity of, for example, 0.9, then the pixel is fast moving, while all of the other values are undefined, because we are just checking the fast positive moving pixels. It's the same for the third model, but here we are checking the fast negative moving pixels. And instead of 0.7, we are looking for -0.7. So now we have our labels and our training set, but usually when the interferogram comes from the platform or from any other model, they come without being sequentially arranged. So let's give these interferograms a sequential, which is chronologically logical. Like for example, instead of having the interferograms this way, we will arrange them according to the dates of their slaves. So for example, we have these interferograms, and these are the dates of the slaves. According to arranging the dates of the slaves ascendingly, the interferogram number 3 will become number 1, and number 1 will become number 3. Okay? We have the atmospheric artifacts, how we can do it. Main power of the low frequency signals comes from the atmospheric artifacts. Accordingly, high pass filtering was recommended enhance the stability of the methodology that can precisely more detect the localized phenomena.
Now we can train. Input all of the data sets and train. No. Because we, as human beings, should have some control on these data sets. We should have some differentiation to know what does that mean. At least I can see by myself, I can check if this pixel is moving up or towards the satellite or far from the satellite. So what we did, we tried just to differentiate at first between the movement, the slow movement and the fast movement. So from the data sets, for example, that contains the negatively moving pixels, we formed two matrices. The first one related to labels of training samples that has velocity values between 0 and minus 0.7. This is a slow movement. Then the second matrix, which is the fast movement, contains training samples that has labels related to the fast negative moving pixels. The velocity value is less than minus 0.7. And here we can see these matrices. The slow movement has training samples that it's more than training samples, and of course we should just clarify something, that what's the white data points mean and what's the black data points mean. So when we see any white data point, that means that this space value is between 0 and 1, and when we see the data point is black, that means the phase value between 1 and 2 pi. And here it's important to mention that we changed the range from minus 5 pi to become between 0 and 2 pi. So we can see that the slow movement contains more white and more training samples that has phase values between 0 and 1 pi. It's the same pattern existed in most from data sets. And we can see that the slow movement matrix is much more white, has much more white data points than the fast. So much more phase values between 0 and 1. It's the same for Lisbon, but actually here it was not that much clear because the data points were too much stick to each other, so that algorithm had difficulty in that differentiation, but still existed. And here the statistical evaluation says that as well. When we train this model, this is the preliminary results that we got. And actually, we can see that the most important models were cubic SVM and cosine KNN, the k-nearest neighbor as a support vector machine. But the cubic SVM was missed in Lisbon for the model positive and negative. But please notice that even with that we have 90% and 80%, there was percents between 74 and 75. That's not that much satisfying. So before we move to the enhancement of these results, I would say that we compared cubic SVM and cosine KNN to know which one we should use. And by the comparison, we chose cosine KNN, preferred it over the cubic SVM. To enhance the results, the principle of pseudo-leveling was very helpful, and it was actually simple. We trained the model. The model has low accuracy, but we don't have any other label data set to enhance the model. So we created data set of measurement points that has an overall coherence, which is no less than a threshold of 0.7. This trained model has been tested on this data set. When the prediction is 0.9, that means we have a very high prediction value. And this is trusted. So we can give the label and then train the model again depending on the pseudo label, because these labels are not true, and get another prediction. Of course, we should, after we take these labels, we should take them from the test set. We can see that sometimes we needed 2 iterations, sometimes we needed 3 iterations, and we moved from 74, for example, to 97. This is the results of 3 different models, of 3 different data sets, and these are the confusion matrices that confirm also these accuracies. Finally, the remote sensing and ArcGIS are so mixed, so let's compare. In the environment of ArcGIS,
guess the ground truth and the test set. Here we can see the top figure is the figure that contains the ground truth, and in the bottom the figure that contains the test set. Very similar. Also the same for another model in Washington. Very similar and less difference. The same also for Lisbon, another different model. Again, we interpolated these measurement points and masked the road existed there to get a prediction of the index of the risk for the roads there. So if the value, for example, in the first model was 1, that means these roads are undefined, classified as undefined. -1 means the fast positive movement. And also for the high negative roads in Washington, we have also -1 means high negative, and also the other are undefined, while for Lisbon, we have the green for the negative and the red for the positive. Finally, yes, artificial intelligence, particularly machine learning, is effective for learning displacement signals. Of course, we are just predicting on 3 different regions of the world. More exploration is needed. But these are the numbers that we've got, and we are open to any kind of suggestions or criticism. And then cosine KNN was the best model, and it has also a generalization ability, so we do recommend it. The low validation accuracy has been enhanced by pseudo-labeling. And finally, as an answer for a question test in the round table that was asked, like what can persistent scatterer interferometry do for artificial intelligence? We recommend to test this procedure in this domain. Thank you so much.
Thank you, Lama. We have time for questions, please.
Okay, thank you. Nice talk. How much the method is sensitive to the number of training samples if you increase or decrease the number of training samples?
A lot. Not only for the number of the training samples, but also to the distribution of these training samples. So as much as they are stick, then the change in the phase is more slight, so the differentiation is harder.
Okay, and have you tried to apply the trained model from one data set to another?
Yes, and we actually couldn't, because either when this will be successful, when this Earth is changing, it has the same change rate like that Earth. Because finally what the algorithm can predict is the same pattern. So if you are in Lisbon, for example, and you have fast movement, and you train the algorithm for the fast movement, while you are in Lombardy and the movement is slow, so how can the algorithm learn? That's why we, after making lots of predictions and lots of testing, maybe we can get all of these patterns, as much as patterns we can get, as much as the strong prediction we would get as well.
Okay, thank you.
More questions? So maybe I have one. Or maybe two. So one is, first of all, thanks for the nice talk, also from my side. So you benchmarked different machine learning methods,
Yes.
and you come up that the cosine KNN is the best one.
Yes.
Can you comment? So can you comment on why you think? Is there some reason, or is it treated all the black box? So all the different algorithms that you tested, or is there some reason that you could exploit also to improve the algorithm?
Yes, of course. Because cosine KNN, first of all, it's known with its ability to generalize the prediction. This is one most important thing. Then when it predicts, it just calculates the similarity between the faces. So for example, I have numbers like 1, 2, 3, 4, And then I have, for example, 4, 7, 9. So this classifier can know the pattern, how these numbers is has very important ability to know how these numbers are changing. Okay. So the similarity of this change, and if we have another row that has the similar change between these numbers, he can capture it very well.
Okay, thank you. And the second question would be, you have set some threshold of the 0.7 centimeters per year. Is there a specific reason on this value, and or did you test a different threshold? Could you observe differences, or could one think of get rid of this threshold and let the whole process be done by the machine learning alone without any pre-selection, so to say?
Thank you so much. This is a very also important question, because yes, the threshold affects. The threshold affects, and when we, for example, tried to train the model for 0.3, because we said that we were a very sensitive model for just 3 millimeters, but we couldn't get these important results. And why 0.7? Because if we can come back to a deformation map, we can see that the color, which is green, that becomes from green, 0, to blue, 1 centimeter, starts to have this change, I would say, at 0.7. So yes, at 0.7 we have recognizable movement. We can see it now here if from any deformation map. So it's not just me, but also previous scientists have this.
Thank you. So, Sam, you wanted to raise a question or no?
I'd have a quick question about the high-pass filtering for removing atmospheric artifacts. Had you considered perhaps ignoring that pre-processing step, leaving it in, and particularly for maybe models like neural networks with enough labels, it would have learned to ignore stuff like that? Or what would be the worth of doing something like that?
So why, you mean why we did that, why it's important to do that? Or
whether you'd considered just doing less pre-processing and allowing the model to do it more in a data-driven way?
Actually, it's for the first stage, because as we know, the algorithm can learn the pattern easily. It's how the machine learning works. It's just get the pattern of these training samples, and you may at the first time say that, okay, these measurement points has been excluded from a time series, so it's already processed and it's already filtered and everything is fine. So why you want to filter? Because when I want to use the pseudo labeling, I want to collect a data set, and this data set, instead of saying that, okay, this data set has a coherence threshold, as we said, of 0.7, but also it has this layer of complexity. So why we cannot just give another important criteria, like we are more confident of these pixels, that they have less low pass component, that this is not an atmosphere that makes these changes, just like for that.
Okay, thank you.
You're welcome.
Thank you, Lama. So we move now to the next speaker, who is Carolina Pagli from University of Pisa, with a talk on the use of deep transformers to improve spatial coverage of INSAR velocity map.
Hello, good morning. I'm really here presenting on behalf of Diana Orlandi, and she really wished she could be here, but she's expecting for November, so you only get me today. And this is very much part, of her broad PhD study, which is to apply artificial intelligence, different methods to environmental hydrological problems, and then deliver some simple tools for national agency that can also be used. This is mainly being developed also at the Department of Computer Science of the University of Pisa. And the aim of this is because, artificial intelligence is quite a lot used now in science, but the local agency, they don't find these too easy enough to be used. So the aim of her PhD is just to... Yeah, okay. And anyway, the first environmental hydrogeological problem that Diana wanted to solve is about land subsidence. Land subsidence is a major problem at least in the northern sector of Italy, and has been traditionally studied with sparse or unlimited time data set like piezometric measurements at a few sites. But it fits INTER very well, and then more recently we see lots of study of land subsidence with INTER. And in this figure you can see this is a town in northern Italy which is experiencing quite strong subsidence, and that's not the only case. Land subsidence here being defined as both a gentle or a sudden sinking of the ground, and it can be caused by natural events as much as by tectonics and anthropogenic. Most of the causes of subsidence we see in Italy, which are the subject of this study, are caused by either water pumping for irrigation or for industrial purposes. And this land subsidence obviously has a strong impact, or potentially strong impact, on the infrastructure, and hence the importance the local agency give to this aspect. It's not just in Italy that there's strong subsidence. As you see globally, there's been also casualties and very strong subsidence in Mexico City, for instance, or other sector in East Asia. This study area here, we decided to study the town of Carpi, which may not be globally known, but it's this small town here in the Po Plain, which is a sedimentary basin just north of the northern sector of the Apennine, which is here. And in the Po Plain, there's several cities, even bigger cities, that for a long time have experienced quite significant subsidence, like Bologna, Reggio Emilia, and other important cities. Here, the extraction of the groundwater is mainly for industrial usage, and we selected Carpi because it's particularly sensitive as it is both farmed, heavily urbanized, and heavily industrialized. So Diana started by studying the subsidence with INTER, and she applied two methods, both SBUS using the TAP geohazard platform, which is also thanked here, and stamps. So here you see the results of one of our geometry, in particular is the ascending for the whole, practically northern sector of the Po Plain, which is here, but also part of the other side of the Apennines. And as you can see, the period is from 2017 to 2021. And while the SBUS modeling she did is quite standard, here I reported the SRTM she used and the coherence threshold. But this could be something that even a local agency sort of could produce by using the TAP, so it's a simplified SBUS flowchart. And nevertheless, we could get, even with sort of the standard parameters, quite a good signal in the Po Plain. You see Bologna, the subsidence here, it's not the earthquake, and then Reggio Emilia and Modena, but also the subsidence I showed you before in Pistoia, and here, interestingly, that's Larderello geothermal power plant where they reinject part of the fluids they extract, but clearly not enough to balance the subsidence. And she chose a study area, this one, it's Carpi, in fact. And here you can see that this area, we are aware there's subsidence, but the coherence is clearly not great. And so she plotted also the pattern of the time evolving deformation, which is also just a standard output product of SBUS and can be easily found also by national agents. And for 1 pixel at where there's the red triangle, so you see that clearly this type of subsidence is fairly regular. So whatever they're pumping fairly constantly and no intention of stopping. And then she also processed the other orbit, so it's very similar pattern, again, subsidence, maybe a little bit more coherent, slightly different rate. Here we go up to 5 centimeters per year. The previous one was 3.6, but it's still pretty important rate of subsidence. And again, even here, it's a linear subsidence pattern. Then she also tried with SPAS, just in the attempt to see if different methods could also lead to different level of subsidence, of coherence, if that's just a matter of if you use distributed or permanent scatter. But the end of the story is no, even, with the percentage scatter, she just downloaded the stamp, and you can see that the coherence is not very good. And so there's lots of areas that are very incoherent. So the aim here was to try to use one of the deep learning technique to the main aim of trying to find out in a more clever way, which is not just interpolating, what is the subsidence in the pixels that are not coherent by using the time series. So what she did is this is the time series that we just get from SBAS. So it's at different epochs, time 0, and then until that was 2017, 2021. So we choose the SBAS for input to the deep learning technique. So as a first attempt to make sort of the data set very homogeneous and easier for the deep transformer to get trained on, she also resampled it to 100 by 100 meter pixel, and then she took every single epoch, then masked the pixel and aggregated all the data using a common masking area, just so that she was sure for this test to select only the pixels that are always coherent. It's not strictly necessary, for the deep learning, and I think also an improvement would have been to maybe even use the incremental time series to make sure that every different epoch you actually use the most pixels that are coherent at a given time. Then she started the pre-processing, which consists in these steps. So practically at the previous steps, we just created a sparse matrix, and that's our machine learning data set originally. But they also did some more tweaks and tuning. First, they did a random selection, which means they took the original image of the subsidence at a given epoch, and then they took tiles. They made them into tiles, which are 20 by 20 cells, so about 2 by 2 kilometers. And then they decided that if within the tiles they didn't have at least 100 coherent pixels, then they would discard that for the machine learning analysis. And if instead you have more than 100 non-null pixels, then they would use this submatrix to create the vectorial record, which is exactly what is the input to the deep learning, and I'll come to that later. They also decided to limit the batch, which is somehow not clear to everyone, because in the tiles it can be full, right? So you can have, say, 400 pixels that are perfectly coherent, but just not to have some pixel, not to weight too much pixel that have a lot of coherence compared to the other, they limit the uppermost number to 300. So if they had the tiles with 400 records, they still downsampled randomly to only take 300. This also is obviously convenient for computational reasons. And then once this is done, they create the so-called vectorial record, where it's written there, vectorial transform, which is a simple step whereby you order your data within each epoch in a vector that has first the coordinates for each point, as you see here, and then the subsidence or the value of the pixel. Of course, we are talking about interferograms that have been completely unwrapped. And so then this defines their machine learning data set that has been then divided into two. 80% has been used for training and 20% has been used for testing. So training of what? We are trying to train the deep transformer to learn how to use some of the value of at the given coordinate to learn the others. And this is the architecture they chose. So the problem is really a simple regression problem where you see you know the coordinates and say the subsidence at a given pixel, and you want to know it at a pixel whose coordinates are known but not the value. And for that, they chose the transformer because it adapts very well to sequential records. And differently from convolutional neural network, it doesn't need to have all the points coherent. You can have as many holes as you want. And this simple equation, you can predict also the point where you know the value, which is what you do during training. But you also can predict the point where you don't know the value. And you can predict as many value as you want. They also chose a particular architecture of deep transform, which is called causal language modeling, which is actually an architecture normally used for text, for analysis of text, like ChatGPT uses it. And they sort of mask part of the text just to get what's the most important part. So the algorithm does the same with the pixel. It masks part of it to learn how to predict the other. And yes, it also is an advantage because this causal language modeling has a self-attention mechanism, which means we don't have to worry ourselves about the weighting of the different tokens, the different pixels. It just it does all the statistics within itself. And so here is the architecture they used, and then finally the results. So after these are the results where we, on the testing data set, this 20%, for the pixel, of course, that are always coherent. So where we could compare the prediction of the machine learning to the original data. And I compare to KNN, which they tell me is the most simple thing instead. And the mean absolute error of the transformer here is plotted against the dimension of the input, because as I said, we had input that are very big to very small, and you can see that the transformer performs significantly better than KNN. But other than that simple exercise, why did we want to use that? Is that once the transformer is trained, you can give it as an input any data at any epoch. For instance, here we gave him an epoch in June 2019, which is the data where on my right, where it's written original. And then once the algorithm was trained, it can tell you what's the value of the pixel at all the missing bits. Of course, to do that, we practically just run iteratively the deep transformer very many times. One approach is to just predict the value for a few pixels, then feed it back in, predict the other pixel, which is what we did to fill up. In this example, we wanted to fill up completely the holes, and it's on the left. And it works fairly well. We also try for another geometry. Again, you can use the same training and get a perfectly filled matrix. So to conclude, and some potential remarks, this is a simple example of just seeing how the deep transformer works. It works very well for sequential data, so you can also have the flexibility of predicting only a few pixels, so only a few holes, or as we wanted maybe to show in this example, filled up everything. And we have a simple example where the deformation was linear, but you can think of training your deep transformer to different portion of your time series. So you have, a pattern for 2021, if it changes for 2023, and so forth. So we think that once it's trained, it's easier to give to the national agency, sort of to predict or just trying to fill in the data. The last thing is that with this method, that in the equation of the transformer, you can predict an existing value. So if it works well, it will tell you a value that's similar to what's been measured, or also a missing one. And so my potential improvement are that here, to run it quickly, we just only took the common part of the time series, but I would guess it's not the best. Because if you use instead the incremental time series, you'll have that sometimes different parts of the interferograms are coherent, maybe sometimes even where there's a systematic holes. While if you give him something where the hole is systematic, it's going to fill up just based on the rest of the subsidence field. And yes, and also we didn't have anything to validate, but I suppose one other test could be to compare to GPS value. And it's also fairly, I think it can be fairly useful, because when we use the platform like TAP or the others, you have very limited availability to tune and tweak the parameters. So you can't really get sometimes better coherence that what comes out from these platforms. So this could be an alternative to redo a lot of the time series yourself. And this software is also available on GitHub if you want to try. Thanks.
Thank you very much. Do we have any questions?
So for validation, did you think about taking the GPS as input value to feel the thing and compare with SAW data and to see if you rebuild the SAW data?
Yes, I hear the limitation of this is that you are training with the far field, say, because the inner part of the substance is never coherent. So it would be nice to compare, maybe if you had a few GPS points exactly in the center, that could have been an independent measurement to validate the results. That's what I meant.
There was some raised hand, or if not, then thank you very much.
Thank you very much.
Carolina.
Okay, I'm now pleased to introduce my co-chair, Michele Martoni. Over to you.
So, good morning, everyone. Today I'm gonna present to give a talk about a topic which is maybe less related to applications, but still it has a significant impact on the resulting performance and quality of SAR and INSAR products, which is the compression of the SAR raw data. So the title of the presentation is of exploiting artificial intelligence for performance optimized raw data quantization in SAR and INSAR systems. I want to acknowledge my colleague Nicola Gollin, Paolo Rizzoli, and Gerhard Krieger from the German Aerospace Centers. So just to give a context and motivation of the work, we have been seeing in the last days all the really amazing programs for new and future and present and future SAR missions which have been programmed not only by ESA but also by other institutions. And yeah, the trend is clear. So we are going to have in the present and near future systems which are more and more complex, equipped with multi-channel and multipolarization, are also multi-static configuration with multiple sensors, and also are capable to offer to achieve a final resolution at the same time a wider swath with compared to conventional SAR. And at the bottom of the slide, you can see what are the performance in terms of achievable swath width and resolution of a conventional SAR, and how these dramatically, so how the increase by 1 order of magnitude or more if going to, let's say, as an example, multi-azimuth channel architectures. To have more data is, of course, nice for a variety, all the application and scientists and users, but at the same time poses, in terms of system design and mission feasibility, dramatic constraints in terms of the storage and downlink capability of the system.
in fact, the data rate is proportionally linked to all the parameters I've been listing before in terms of, for example, number of channels, number of satellites, and also resolution and swath width. So this poses a clear trend in terms of larger data rate which are required by the system, and at the same time harder requirements for onboard memory and downlink capacity. In this scenario, the quantization of the SAR raw data plays a key role, since it affects, on the one hand, the amount of data to be handled, of course, but also it directly impacts the quality of the resulting SAR products. So there is a need for, and which is even more urgent for the future scenarios, SAR mission scenarios, for efficient resource allocation strategy. This will allow, on the one hand, the performance to be aligned with the requirement in terms of data quality and also mission duration. And as an example, I have been working for the Tandemix mission, and we had also several constraints for the downlink and data acquisition, which basically drove the duration of the global DM acquisition. In fact, for one global DM coverage, we needed more than 1 year. So just to also to clarify let's say the workflow we are working with, starting from the SAR data acquisition until to the generation of SAR and the higher level products. Basically the SAR signal, the received echo, is first sampled and then quantized on board and stored before being downlinked to ground. And these are the, let's say, the bottleneck which we are dealing with, and I'm going to act on the quantization of the raw SAR signal. So we don't deal in this specific talk with onboard process data, but we leave the data as they are, raw, and then compress them in a more efficient way, and then downlink to ground. Just to give it a short, quick context also in terms of state-of-the-art for current SAR data compression algorithms. So the most used, I would say the reference raw data quantization scheme is the so-called block adaptive quantization, which is being used on basically all the SAR missions so far, and it basically adapts. The quantizer is able to adapt to the local statistics to the raw data in order to set the decision level. So you can see, for in case of a low power signal, then the quantizer is shrinked, so to say, while it adapts in case of a high power signal is received. Typically for SAR systems, raw bit rate between 2 and 6 bits per sample are used, while 2-bit is very low and provides very poor performance, while 6-bit is in most cases unfeasible for the resulting data rate. And then for the Sentinel systems, the FDBAQ, the flexible dynamic BAQ, was also developed, which adapts on board the selection of the bit rate depending on the power of the received raw data block. In general, it is often assumed that the quantization errors can be modeled as let's say, signal, so error source, which is uncorrelated to the SAR image, so as an additive white Gaussian noise source. This is actually true only for homogeneous target, since if we look at real data, here you can see, yeah, it's quite some information to maybe to comment. So on the left, you see basically a plot showing the standard deviation of the phase error calculated for different scenes, which are different SAR scenes, which are each one represents by one vertical, let's say, set of points here, because each scene is classified by a different so-called degree of heterogeneity in the backscatter distribution. And one can see each dot, each color represents a different quantization rate. And we can see that if going from a homogeneous to a heterogeneous scene, the quantization degradation, so the impact of raw data quantization in the resulting INSAR phase error dramatically increases. So if, for example, we set a requirement of 10 degrees shown by the brown horizontal line, we can live with a sort of 2 bit per sample for homogeneous, but we need up to 4, so more than 100% more data in order to fulfill the same requirement. And on the right, you see basically the table representing the required bit rate for the different scenes for a requirement of 5 and 10 degrees phase error requirements. So there is, as it is visible, a significant impact of local backscatter characteristics on quantization performance. This can be also seen here. This is a tandem mix scene over Mexico City, and what you see here is the phase error solely due to quantization. So this is a phase error map comparing uncompressed and compressed interferograms, compressed in terms of quantized. And if one look at the statistics, this would result in height error, so in the DM height error increasing by several meters. So then putting to the risk the fulfillment of height error requirements on certain heterogeneous region. On the other hand, the raw data of this image look like this, the small image on the right. So the problem of raw data, so to say, is that there is no clear, differently from optical image, for example, it is hard to find correlation within the data. So other more effective algorithms like JPEG or wavelet-based could not be exploited. So on the other hand, there is the need of advanced compression methods to adapt the SAR performance degradation, because as we've seen, this can dramatically impact the resulting performance. This novel approach could improve, and many applications could benefit from them in order to get a more homogeneous and ultimately to improve, for example, the quality of the high-level products, so information retrieval, like, for example, land cover classification or, as an example, deformation on soil moisture. So what we propose is to move from in the case of constant BAQ, so to move from a constant BAQ rate scenario, so constant BAQ, where we have an heterogeneous performance, which is shown on the right. This is the signal to noise quantization, so it's basically the SNR of the quantizer. And here at the bottom, you see bottom right, you see the histogram, so the distribution of the resulting error map. In particular, the SQNR is defined as basically the power of the input signal and the power of the quantization error, so the difference between the uncompressed and compressed signal. And we move from this scenario to a sort of performance optimized BAQ, where we define a bitrate map, which is then able, if applied to the raw data, to fulfill the given target requirements. In this case, for a target SQNR of 10 dB, then one can see that more homogeneous performance can be achieved. And so, in this way, a joint adaptation and optimization of data rate and performance can be achieved. These are examples based on the Mexico City backscatter map that you can see for 10, 15, and 20 dB. Of course, the higher the requirement, the higher the resulting bit rate. A quick comment on the SQNR. This is used as a reference, let's say, metrics for performance assessment, as have defined this parameter, so this quantity before, so it's the ratio between the input signal and the quantization noise, and this can be also related to the total, to the overall SNR, so linking the quantization noise to the thermal noise, and the plot here basically shows the impact of the total SNR as a function of SQNR for different signal to thermal noise ratios, so basically different backscatter levels. And this can also be linked to the resulting coherence loss. And from our experience, this is also an error source which is maybe not always considered in the modeling of INSAR error, but for homogeneous scenarios, this can be maybe goes from 1 to 5%, but in case of heterogeneous scenarios like the urban areas that I've shown before, this can rise up to 10 or 15%. So it may have a significant impact on the resulting performance. And this, as an example, you can see the performance optimized BAQ applied to TerraSAR-X global backscatter map for different requirements of 15 and 20 dB of SQNR. And you can see also if fixing one requirement, the variation of the bit rate, for example, going to a more highly heterogeneous area like highly rugged terrain or forest area. The limitation of this method is that we need a priori knowledge of the scene. So because, as I shown before, this basically, the bitrate map is based on the backscatter that is underlying of the acquired scene. And this is, although there is a huge availability of backscatter maps, due to the rapid changes, as for example, over snow, ice areas, seasonal effects, this may not always reflect the available backscatter information to model the actual backscatter distribution which is being acquired by the SAR sensor. So we have been developing this activity in the frame of ESA study focused on the exploitation of artificial intelligence for SAR data compression. We've been doing this study is currently ongoing together with the University of Bucharest and Airbus. And the main goal of this project is to develop, to exploit the deep learning in order to derive, to optimize the bit rate before onboard data compression in order to control, to tune, to adapt the performance in the resulting SAR and INSAR products. So for this, we consider this as a self-supervised regression task where the bit rate has to be defined, so derived by the machine learning algorithm. And for this, we use standard CNN-based architectures, which has been shown to provide so good results also for other applications. So the definition of the goal of the let's say of the method is to define a deep learning architecture to derive the required bitrate without a priori scene knowledge. So for this, the idea is to have therefore a raw data matrix, which is ideally acquired on board, and then a deep learning architecture is able to derive the bitrate at low resolution. For this, how to derive in a proper way, we need a consistent training phase where we exploit reference data which through which we can model and then predict the resulting quantization error in the raw data. So the reference bitrate map generation, for this we used a series of uncompressed tandem mix acquisition. So by static acquisition acquired with the full quantization resolution, 8 bit per sample, which have a negligible quantization errors. And we recompress this on ground. You can see that we try to cover very different land cover types. So going from soil and rock and snow, ice, forests, and also urban areas. And we divided these. We used some of those for testing and some for training. And as I said, we requantized on ground to the available quantization rate. We processed them, and we then basically could carry out a performance assessment in order to derive for each requirement a bitrate map which would fulfill the given specification. So, for example, and of course, for this we take the minimum bitrate in order to optimize, so to minimize the resulting data volume. In particular, we allow also the implementation of fractional bitrate, because although the BAQ is able to quantize data only with integer rate, thanks to the SAR acquisition principle and the focusing operation, if let's say, one can synthesize fractional bit rate by opportunely toggling the integer BAQ rate. For example, in order to get 2.5 bit, one could toggle between 2 and 3, so have a proper lookup table doing this on board. And in the end, after the focusing, the resulting performance would be equivalent as having the target fractional bit rate. So this is also in order to increase granularity of the system and to achieve more targeted performance. So then we move to the inference, which, as I've shown before, once that the reference bit rate are generated and used for the training phase, then we can let's say proceed with the inference case, inference stage. We give as an input new raw data, and we feed this into the deep learning architecture, and out of this we get which adaptively quantized the raw data according to the trained network, and out of this we get so the method we called AI BAQ as a reference, and out of this we get the quantized raw data. For each block, as I said, the standard BAQ is used with the let's say integer BAQ, integer rate. So just a few examples. Over the Mexico City, this would be the so-called reference, the true, starting from the bitrate map generation, and this would be the outcome of the deep learning. So one can see that at least large scale difference, that's going from south to north, there is a variation in terms of land cover, can be let's say can be catched by the network, although there is still some let's say finer details which is not fully let's say properly learned by the and catched by the architecture. And here you can see the error bit rate in the histogram at the bottom. So the average is well, there is no significant bias, almost zero mean the error, but still there is some let's say dispersion in the bitrate allocation, which is given by the high heterogeneity of the scene. And similarly, we also consider a more homogeneous scene, like the Greenland, which is very, let's say, ice and constant backscatter. And also for this, we could get some maybe a noisy map. But as I said before, then when going to quantize the data effectively, then already during the SAR focusing, a sort of average is obtained. And also in this case, we get a relatively small dispersion. Then finally, we need to assess the performance to assess in the resulting SAR images what's the effect and the effect of the degradation that it is achieved by the proposed method. And for this, we compared the standard BAQ and also the FTBAQ implemented on Sentinel. We tested on TandemX data, which of course is not designed for. So we had to manually tune the FTBAQ because it also involves the use of backscatter map and the lookup table. So this was somehow, yeah, and I would say is not the one-to-one algorithm corresponding to the one which is, or at least the bitrate selection corresponding to the Sentinel-1, but we could at least benchmark the methods. And what you can see here are the SQNR maps. On the left is a constant BAQ with 4 bit per sample, and you can see that there's a good performance, but also high heterogeneity. And similarly for FTBAQ, which privilege high power scatterers, like for example for PS analysis, and so in the bright targets in the scene are privileged and the higher bitrate are allocated, while our proposed method is able to achieve a more homogeneous performance for, in the case, 15 bit per sample. And here there are also the histograms, and one can also appreciate the fact that for the AI BAQ on the right, the resulting distribution is more shrinked around the target performance requirement. So summarizing, we tested this on several test sites. giving two SQNR requirements and also different methods over different scenes. You see Greenland, Uyuni, Las Vegas, and Mexico City, and with the colors is basically reflecting how well the target performance is achieved. And of course, constant BAQ and FTBAQ do not adapt to the target final, to the resulting SAR performance requirement. They are not designed for this, so let's say it's fine. But what we would like to highlight is that the proposed AI BAQ is, on the other hand, able to follow more, so I would say better, the target requirements, and in this way to also to adapt the target bit rates. As an example, if one would stick to, for example, 10 dB SQNR, a significant saving in terms of bit rate could be offered by the proposed AI BAQ of almost 1 bit, which would result in a data volume reduction of up to 30%. So this is for one specific scenario, but I would say the main message is that the proposed method could be better used to better tuned to the actual performance, which can be application specific. Okay, summarizing, I'm coming to the conclusion of my presentation. So we have presented a novel AI-based SAR data compression method for the joint optimization of data rate and SAR image performance. And for this method, no a priori knowledge of the backscatter scene is required. This method can be used in combination of other data volume reduction approach, like for example, transform on predictive coding based, if the SAR sensor makes this possible for data compression. We have seen promising results, but of course they have been to be further investigated, maybe also outside of this project as the mentioned project as a research activity to investigate potential improvements. And also we want to investigate possible hardware implementation, which are currently being investigated by the colleagues in Airbus. And also the method should be tested on other performance parameters to show that it is able to, let's say, to tune and to fit with different also INSAR and maybe also higher level products requirements. And last but not least, yeah, we are being filed the patents and being for describing this method and being waiting for approval. So with this, I conclude my talk, and thank you very much for the attention, and we'll be happy to take any questions.
Okay, thank you very much. I think we've got time for one quick question.
Hello, thank you very much for your talk. That was very interesting. This might be a little bit tangential as a question, but given you the demand of given that you have this demand where you try to minimize the amount of data that you have to transfer, have you perhaps considered looking at things like compressed sampling or compressive sensing in the context of SAR?
Short, thanks for the questions. This is a very interesting aspect, I would say, to look at. For compressive sensing, so I would think to need to first focus the SAR image on board, and then maybe to being able to exploit this in a more effective way. Also, compressive sensing exploit in this sparser presentation to look for some pattern in the data and this it is probably worth taking a look at it, but as I shown before, raw data mostly look like noise, so it is probably hard to have a significant saving in this direction. But thanks for the comment. We will look at this.
So I see several chairpersons in this room. My colleagues tell me that we are still missing many summary presentation slides. The summary session starts at, if I remember correctly, 11:30. So please send us your slides and get ready to be sent. Thank you.
thanks for the reminder. We will be trying to do as fast as possible for our session. Okay, thank you, and we would then proceed with the last talk of the session, which will be held by my DLR colleague Riccardo Dalmolin on the exploitation of deep learning for forest monitoring.
So thank you very much. My name is Riccardo Dalmolin, and I'm doing my PhD in a partnership between the German Aerospace Center, DLR, and the Sondra Lab from the Zentrale Supelec University. And today I'm going to be talking about our deep learning framework for monitoring the Amazon forest with Sentinel-1 INSAR data, and mainly regarding the seasonal challenges we faced when moving also to a large scale. So a bit about the motivation of our work. It's needless to say the importance of monitoring forest ecosystems in the context of environmental policy making and also climate change mitigation. Here you can see, for example, how the deforestation has been advancing in the Brazilian Amazon forest between 2008 and 2021 based on data from PRODES, which is the program for calculating deforestation from the Brazilian agencies. And what you can see here is that in these past years, we've had a total deforestation estimated in more than 100,000 square kilometers, which is equivalent to the area of Bulgaria, more or less. So let's talk now about some of the challenges that we have in monitoring the rainforest. As you know, these systems usually rely on optical data, and in the rainforests in particular here in the Amazon, we have a mean annual cloud cover above 70%, which might hinder and dificulty this kind of constant and reliable monitoring. Which means that some of these maps might be only updated once a year during the dry season. Here you can see some examples and in how the deforestation is advancing from 2019 to 2021. And in order to be able to act fast, we might want to update this kind of monitoring faster and with more reliability. And the question is, how do we do it? And what we propose here in this work is to use a short time series of Sentinel-1 INSAR data to quickly have an update on the status of the forest. So we initially defined our region of interest here in the Brazilian state of Rondônia in an area of more than 200 square kilometers, as you can see here in the bottom left of the figure. And this area is one of the most deforested and also consequently studied places in the Amazon regarding deforestation and land use changes. And that's why in 2019 there was a special campaign with a 6 days repeat pass coverage, which is usually on the base of 12 days only for this part of the world. So we focus on these and select 12 swaths covering a temporal baseline of only 24 days to try and monitor this land cover in a more regular way at a resolution of 50 meters and with single VV polarization. Here you can see our external reference that it shows from the finer resolution observation and monitoring, the global land cover from GLC 2017, which is a thematic map containing 10 land covers with a resolution of 10 meters coming from transfer learning by using the random forests. And here you can see on the figure the metropolitan area of Porto Velho, which is the capital of Rondônia. Here you can clearly see where the city is as an impervious area. We also have some branch of the Amazon River here denoted in blue, and some grasslands and also the forest. And the first feature that we use, and it is from our future interest, is the sour backscatter, which we here denote by the gamma naught coefficient, which is normalized by the area perpendicular to the line of sight of the radar. Next, it is also our interest to compute the interferometric coherence, which is defined as the amplitude of the complex correlation between our interferometric pair. Here you can see that there are several decorrelation factors that contribute to the correlation between a pair of images, being, for example, limiting SNR, quantization errors, ambiguities, calibration errors, and so on. But here talking about repeat pass, Sentinel-1, and land cover classification, we are really interested in the temporal decorrelation that we have for different temporal baselines. So there are several models to try and do this. Here, for example, we have an exponential model which is described by ρLT, which is the long-term coherence, and also a temporal decorrelation tau. So we use these metrics and exploit them to see how different land cover classes decorrelate over time. Here you can see for the same example, for example, the difference between the 6-day coherences and the 24-day coherences. And it becomes clear that these different classes decorrelate differently over time. For example, the impervious areas corresponding to the city remain quite stable, while forest is always, more or less in any temporal baseline, quite decorrelated. And we have some changes specifically when it's concerning grasslands or croplands. So we'll try to explore this to have a better description of this land cover with our short time series. And what we propose to use here is CNN inspired on the UNet, which was originally proposed for medical binary segmentation. And it has this nearly symmetric encoder-decoder in a more or less U-shape, that's why the name. And as we have more and more available data for remote sensing, this is also becoming more attractive for us, especially in SAR. And the advantage that we have in using such models is that with even few input features, we have lots of learnable parameters. You can see here for n input features, we are going to use higher and subsequently more number of convolutional filters to extract feature maps which will have a higher level of description power than the input features that we have, or even manually handcrafted features. So we start at 64 here, for example, and end up at our fifth level of the convolutional neural network with more than 1,000 feature maps. And this encoder path is also known as contraction path because we are sampling only the maximal value with the max pooling to condense the actual important information that we have in the features at the cost of spatial information. So what we do in the UNet is to retrieve this information and maintain our full resolution through skip connections that come from the upper layers of the encoder part. So the limitations that we have is that we require a considerable amount of training data, which in the goal of monitoring the whole Amazon, it shouldn't be a problem because we are talking an area of millions of square kilometers. The second challenge is the patch-based nature that we have for this type of learning, which makes it more difficult for balancing our data set. And finally, an up-to fine-tuning is always challenging, but we train our network from scratch, and we can tackle some of these problems. So when we look at landscape in the Amazon region, even when we are not looking at the central Amazon or a really dense forest part, we already see that there is a high class imbalance anyway. So what we do first is to simplify our classification problem to 3 classes of interest only initially, which are forest, of course, for monitoring deforestation in long term. And water also has is really important because of the rapidly changing nature that we have in different branches of the Amazon River. and also to keep track of floodings and droughts. And a third class would be the negative class here, so called non-forest regions, NFR. Even by doing so, we can see that we still have a huge imbalance, which could bias our predictions towards the majority class, in this case, especially the forest, but also non-forest regions. So we do some data augmentation and remove some patches from containing mostly forest and non-forest regions to achieve a more or less balanced data set. Of course, it's never going to be perfect when we are talking about patch-based approaches, but it already helps mitigating these kind of problems. Here you can see the entire framework that we have, and by considering time series of only 24 days, we have two options. The first is to use 5 acquisitions with a revisit time of 6 days, which we do have for 2019 in this area. And by doing so, we have more information, of course, but our interest in a large scale is to use 12 days revisit time, which would result in 3 acquisitions only, but this has the potential to be used on a global scale. Here you can see an example of how we would use the backscatter and the interferometric coherences information. So for the SAR backscatter gamma naught, we take the mean of 3 acquisitions. For the 12-day coherences, we also take the mean between the pair of 12-day and also use the 24-day long-term coherence as an input feature. So we define our experimental setup with different kind of features to try and answer a few important questions that we had in mind. And the first one is if our network can actually learn this spatial information and outperform state-of-the-art shallow learner. So we compare our approach with random forests, which may also use even extra features computed to represent the texture information. And the second question we are trying to answer here is if the CNN is able to learn the temporal decorrelation trend by itself. So we don't need to actual model and try to estimate the temporal decorrelation factor and the long-term coherency. We simply use the coherency stacks as they are, so ranging from 6 to 24 days. And finally, we want to see if it's viable to consider the a minimum revisit time of 12 days, so using 12 and 24, which would allow us to move in the future to any place, anytime. So here you can see our results, and as you can see here highlighted in yellow, our best results was when we used solely the coherency stacks instead of the features coming from the model. So the CNN could in fact learn it by itself, but also interesting to notice is that with a minimum revisit time of 12 days already, which allow us to go global, we already have an overall accuracy and F1 score above 90%. So with this, you can see here also an example that we have for a scene comparing the from GLC with our prediction. With this, we can see that at 50 meters already, we can have a good match, and which made us quite motivated to follow up with this approach and made us really think that we are ready to go on the full scale and over the whole year, which of course was not the case. We had some more challenges. As you can see here, we deal with several seasonal effects. When we predict with our model during the dry season versus the wet season, you can see that there's a high difference in the predictions, even though the ground is not changing. So this tells us that this data can be quite affected by the temporal effects. Here you might have an explanation of why this is happening. We have both backscatter and 12-day coherences for the dry and wet season. And what calls attention, of course, we have an attenuation of the dry season, which is higher for the croplands during the dry season than in the wet season, which it's not a problem. But specifically when we look at the 12-day coherences, we can see that both grasslands and croplands can become completely decorrelated, which is a challenge, and we are trying now to see how to address this. So in order to have more data and to be able to tackle this problem, we are now moving to 20 meters resolution, pushing it to the limit more or less. Also with dual VV and VH polarization to have a better description of the classes, and also trying to see if we're able to move to a larger number of classes of interest. Of course, a big challenge that we have is that our reference maps are usually released annually. So we have a single ground truth for the entire year. And if you look here at the predictions, they might be quite different, and we are not sure even when the exact dates are being used for the reference. So we do know that in the case of the Amazon forest, it's usually at the end of July, because that's when the clouds are clearer, but still is a challenge to really ensure that we are looking at the correct and a consistent ground truth throughout the year. So in this case, we can see the different predictions for the wet and dry, and so by taking a look with also visual inspection, we can see that for this case specifically, the predictions were correct, and we did have some changes on ground. But the question remains open, how to deal with it, how to be sure that we have consistent ground truths, and how can we isolate the seasonal components that affect our images and that also may worsen performance or lead to misleading results. So in a further attempt to try and do this, we first mask out potential changes that we have by using some information from the Brazilian agencies such as PRODES and DITER, so we can be more or less sure that we are working with stable areas over time. And of course, another challenge comes from the fact that dry and wet is changing across the Amazon forest, as can change the landscape and the forest and so many factors. So we are basically to construct a robust database sampling data from all these different regions and prioritizing the ones that are expected to be stable over time. So we do this by visual inspection, by masking out these pictures which might be related to changes, and also by focusing on some areas which are demarked as conservation units. So you can see here now when we did this and we tried to isolate and maintain this ground truth reliable for the entire year, a comparison for 5 different classes on the SAR backscatter. This is VV. And what we can see is that in the southern hemisphere winter, which is the dry season, it is much more easy to distinguish between the classes, especially when we are talking about croplands and grasslands. The same happens when we take a look at the coherences. So this is a challenge that affects especially change detection approaches that can only see a change when we reach the dry season, because otherwise the features are too close or too hard to distinguish between themselves, which does not mean that deforestation was taken in the dry season. It's just that it can only detect at that point. So this is a current challenge that we have. And also we can more or less relate this data that we just seen with some precipitation information that we have a historical monthly mean in this region, and in the dry season we can see how much less precipitation you have and how this might be used in the future as ancillary data to also train and make our model more adaptable. Here you can see the first results that we had. In red you can see when we just normally trained our network and tried to apply it over the year. Here once again in yellow you can see the dry season. And versus when we try and use some temporal features which are related to the time of acquisition. So we could in all the cases improve the accuracy, the F1 score by quite a lot. But of course, we did this for a single region inside the Amazon forest, and we now have to be robust to different scenarios, to different areas, and how also to different ways that the dry and wet season express in these different regions. So our final remarks, we could show a potential for mapping the Amazon with data acquired within less than a month, with a spatial resolution as fine as 20 meters, and that our CNN model could learn both temporal decorrelation patterns and texture information by itself, and reach an accuracy above 90% with only 3 acquisitions. So a challenge that we still have is the validation and is the generalization of our model for the entire forest. And to do this, we are also investigating some semi-supervised methods, in particular contrastive learning, to try and isolate the contribution of the seasonal components. We are still working also with data from several different years. We have at this point 5 years of acquisitions from Sentinel-1 to try and reach a better understanding of the seasonal variability that we have and how can this affect our predictions in the end. So thank you very much. I am open for questions.
Thank you, Ricardo. So we have maybe time for one quick question, and then we can move. Please, Carlos.
So thank you very much for this interesting presentation. Just a very simple question. You have used the negative exponential decay model to model the coherence. Which are the other models you have tried to model the coherence? Because you mentioned that this was one of the models.
Yes, actually, this is a work that has been developed at DLR. We have some of the co-authors here. But it's been tried several different models which are more simplified than this one. And by adding a temporal decorrelation factor, it was seen that it had a good agreement with the different baselines that we have for the Sentinel-1. So 6, 12, 18, it was simulated for different temporal baselines, and it was a good fit in terms of features for this case.
Okay, thank you.
Okay, so please, Paolo.
Nice presentation. Probably not. Am I to fire? Okay. You said the model can learn the temporal relationship. You mean exactly the model that you used, or any other type of temporal relationship? And then, since you cannot input the covariance matrix in a temporal ordered way, how do you believe that?
What is meant is that even if we do not use the features from the model themselves, such as the long-term coherence and the temporal decorrelation factor, we still have a higher performance by simply using the temporal the coherences at different temporal baselines. So we imagine that since we are achieving a higher performance, that the network can learn that how to connect these different coherences to the final output. That's the.
Thank you, Ricardo. So now we have our roundtable discussion. We have come up with a few points, seeds questions, based on which we can have then some recommendation to be pointed to ESA. So there are 2 slides. We can start with this, and I don't know if someone wants to start. So we have seen many interesting presentation dealing with machine learning and trying to address different problems, different application, different insert application. Is there any comments on, for example, how could machine learning be exploited? We have seen, for example, one of the talk was showing how can gaps be filled when physical models fail due to, for example, noisy measurements or missing data. That machine learning could be a suitable tool in order to fill these gaps. This is probably one of an attractive solution also for future developments. Or overall, if machine learning could replace in the era of big data currently well-established physical-based models.
Do we have a question top left?
Please, Roman.
Thank you. Yeah, I think as a recommendation to ESA, a lot of machine learning algorithms need training data. I think making an inventory of all the training data sets which are around and collecting that so that other people, other groups can use the same training data set, I think is something that ESA could stimulate.
That's a very good point. Yeah, I fully agree with this. Also to have a common reference, also for all the scientists to have a somehow common data set, hopefully as large as possible, where different scientists from different applications can access.
Good and unbiased data set, because if your data set is not good, if it's biased, you will reproduce a bias in the machine learning. So the importance of the data set is critical for machine learning. So.
Sure.
And having a good data set is very hard.
Yeah, some reference test case could be. Yeah.
I think looking at question 2, how do we encourage machine learning methods especially suited for SAR? It's at least more common to see people taking off-the-shelf deep learning models and applying them to SAR data, but by making the SAR data fit the models, these models that are more appropriate for color images that aren't Earth observation related. What about the other way around, adapting the models to suit the SAR data? So for example, complex neural networks, is it worth the effort? Does anyone have any experience to talk about trying it either way?
Maybe there are still many trials to be done. Please.
Hi. I don't have experience for the SAR, but have experience for the other domain. So there's a way to be able to adjust to try to get the specific architecture or loss function to be able to suitable for the specific data set. For example, if SAR have the more spatial correlate for the noise, so you can define the loss function to be able to cope with that instead of the random noise as as a machine learning that used in natural image is more like random noise. So we should be able to do that. And if you define architecture that make the how it learns to, for example, so SAR itself is quite sparse in data, so you may be able to use some kind of combine the complexive sensings to make it sparse and with the, or cooperate with how other people already present, interpret the data. But I know from my colleague that you guys don't like interpolation because the data may not be interpreted properly and you might inform the wrong information. But however, that would be able to, again, if specifically for deep learning, you can be able to mark some of the data that might be interpreted wrong in the loss function architecture. Yeah, thank you.
Thank
Thanks for the comment.
If I can add something else on the topic of trying to use machine learning and generally various computational methods with SAR, one of the main problems that you've identified there is well, the fact that we're dealing with complex data very often, and in terms of a lot of computational imaging and signal processing algorithms, when it comes to complex data, is a bit of a wild west out there. There's a few people who've been doing work in developing deep learning networks for things like SAR imaging or SAR autofocusing, and those are supposedly developed specifically to handle the complex nature of the data. But the way they do so is not standardized. It's a bit there's even different approaches as how you do simple fundamental things like evaluating a complex gradient in the terms of in the context of a neural network. So if you want to see more machine learning that deals with the more low-level processing of SAR, where we're not simply treating output as a visual image, but rather we're looking at and magnitude data, it might be a good idea to try and standardize processes and have people trained more in the computational aspects of using these kind of techniques with complex data. Because, yeah, as I said, it's quite complicated. I have a student who's trying to convert, to adapt basically an existing network architecture to work with complex data, and it's not as simple as it sounds.
Yeah, thanks for the comment. In general, also, if I can add something, I think we have a lot of researchers doing machine learning on their own. This has been also discussed on different topics, with deformation or soil moisture. So I think it is probably not a bad idea looking at the future to start to coordinate a bit, so to try to benchmark not who is better than who is better at doing something, but at least identifying some algorithm which officially is been acknowledged to work better on some application, and then maybe some more attention, some more focus is coordinated on this in order to overall improve the scientific outcome. So I think it's in this sense also I think ESA could contribute in providing some guidelines, similar as it was proposed for the data set. Okay, so yeah, point number 3, commenting possibly limitations of current SAR and machine learning approach for geoscience problems, and what advance we already know or we think should be needed to happen to realize the full potentials of this technology. Is there missing pieces, or is we are on the right track? Is there any experience that someone would like to share on?
I suppose when it comes to advances, are we more interested in standardizing processes, curating data sets, or are we waiting for architectures to become more readily available to work with this kind of data? What would be the preference?
My point is related to the computational time. Before we say we could share data sets, but we could also share a model, because you could do transfer learnings and then save computational time.
Mm-hmm. Sure.
So it was the point on architecture, but also CNN architecture.
It's a good point about sharing models, actually, with the transfer learning. People might be familiar with pre-trained rates from like ImageNet and stuff, which works with color imagery. In the optical domain for Earth observation, people have done stuff like Big EarthNet, But to my knowledge, no pre-trained model around SAR exists. So if we were to release like pre-trained things for transfer learning.
The last model has been trained, so you could share.
Yeah.
Try to classify something else than forest, for example.
That's fair enough.
Okay, we can move to the next slide. If there are no further comments. So concerning the first point, also trying to say to benchmark opportunities for machine learning based application. Is there say, can one share opinions about is there some applications more say suitable for the exploitation of machine learning based? Could the present algorithms be better improved compared to the current performance? Concerning point number 5, we have already been discussing about also, for example, data and algorithms, a sort of standardization and having a common reference, which I think is a good idea. And last point, not only data compression, but overall there is also a trend on exploiting AI for onboard processing. So this still is a I would say not fully developed or preliminary. There are many studies going on this, but it's also very attractive to carry out full SAR performance and maybe also information extraction on board in order to shorten the latency and reduce the data. So not only in the frame of the current ESA study, like Roselle Harmony, probably would be too late in terms of development phase, but also in terms of future missions, is it probably a good idea also to allocate some effort in investigate possible options for this kind of solutions. So since I'm dealing with this topic, I would say yes. I think I think it's a good idea. I think it is worth. Yeah, also considering the increasing computational capability that can be carried out on board the system. It's definitely also to understand potentials and limitations. Of course, if you try to focus an image on board, get rid of the raw data, then you may have calibration problem and other issues, and this may be difficult to come back and then to reprocess the data. We have been also seeing many discussion on possible reprocessing of Sentinel data due to atmospheric correction. This, of course, is a very risky operation because this approach could prevent somehow a more flexible approach to reprocess to the data. Is there any comment on that?
Top left.
Please.
Yes. Related to I think a lot of people in this community are using SAR stacks to extract particular points within an image and then follow that point over time. So that means that these data sets are reformatted in a different format. So like a big matrix with points and epochs in time. I think the machine learning algorithms are going to add labels to those data sets. So I think as a recommendation to ESA is to study the different data formats that we can use to easily exchange results. So, for example, a particular point may be labeled as a particular feature, like being a bridge or a street or a house. And it would be nice if we could exchange results in the same data format. So we need an efficient data format that can add labels to existing time series, for example, which we can share with each other and develop software that can read those formats. So the recommendation to ESA is to foster that, or maybe to
Thanks, is a fair point. Please.
Thank you. I just have a comment in correspond to Ramon's previous comment on the data sharing. So as a matter of fact, I was looking into my, and so we actually do already have a lot of this kind of training data set from this Chinese website. So for example, now I'm looking at this called Journal of Radars, and I can already see there's an English website. There's already 12 different training data set. And I look into it, actually a lot of the training data set is actually for example, Terasaur X. And so now it's basically more amplitude oriented, like shapes or like different objects. But I mean, there's already a lot of things going on there, and we're already sharing a lot of the data, and it's very easy to download and use. So my recommendation for ESA would be that we could, for example, just pass on the links and encourage people to use, so that we can all take the most out of this already existed training data. And yeah, I never looked at this before because I'm not really an AI guy, but now I'm looking into this website and it's really nice, and there's already a lot of things. Just with one click, you can already get a lot of data set. Okay.
Thanks. Is there any other comment that you would like to share? So if it's not the case, then I thank you everyone for the attendance, and also for sharing and for participating to the roundtable. We will now try, together with Samuel, try to summarize, and then in a session summary and recommendation to be presented the upcoming session summary session. So thank you very much, and thank you for coming to Fringe, and I wish you a pleasant trip back.